Dynamics of a rigid rotor mounted on discontinuously nonlinear elastic supports by Nielsen Barr, Department of Engineering, King's College, University of Aberdeen. The equations of motion of a rigid rotor mounted at both ends is discontinuously nonlinear supports and subject to excitation by arbitrary imbalance are presented. The method used to solve the equations are described briefly, and the responses obtained from the model and an experimental rig are discussed and compared. Good correlation is found over a range of shaft speed, the presence of aperiodic responses categorized by spectral sidebands, which diverge with increasing shaft speed is noted. An explanation of the mechanism generating these sidebands is advanced. So read about rotor models. So in the past, various aspects of the effects of bearing clearance and rotor stator rubs on the vibration response of rotor systems have been examined. In general, most of these studies have considered either synchronous or subharmonic motion, although the presence of aperiodic whirl of a stator in a rotor stator rub system and aperiodic nonlinear motion of a Jeffcott shaft model with a bearing clearance have been shown. So in the rotor model, the model consists of a 4-degree of freedom asymmetric rigid rotor whose motion is described by the coordinate system. Numerical integration techniques. Due to the discontinuous nature of the equations of motion of the system, solution by analytical or approximate techniques is either unwieldy or impractical, and recourse must be made to a numerical means of solution. This, however, necessitates a piecewise solution of the equations. Consequently, the transitions between those segments of the response calculated using the linear model and those computed using the equations of motion appropriate when in contact with the secondary springs must be accurately located in time. 4. Spectral analysis. The response of the system was subjected to standard spectral analysis techniques to obtain its spectral content. In order to reduce the problem of leakage, the Hanning window was applied to all time records prior to performing the last Fourier transform. The spectra themselves were calculated on the basis of the true amplitudes of the components rather than the more commonly used RMS value of the power spectral density. This has the advantage that the response amplitudes may be compared directly with such physical quantities as the radial clearance. The computed spectra were subsequently plotted in the form of waterfall plots. Read about experimental studies. To permit comparison with the theoretical results, a mechanical rig was designed and built. Read about the results and discussion. Nonlinear aperiodic responses. Having seen how sidebands appear in the response of both the model and the rig, it is relevant to investigate these phenomena further by considering a particular case in detail. Sideband generation. Having ascertained that the radial motion of this type of response can be periodic and that the phase between the imbalance force and the radial motion undergoes cyclic variations, this raises further questions as to the origins of the sidebands and what determines their relative magnitudes. Read about the phase plane diagram. The periodic form of the radial motion and the phase between the force and the response suggests that Plotting of an orbit in these or similar coordinates will greatly simplify the form of the motion. In conclusion, good agreement is found between the responses obtained from integration of the equations of motion of the rotor system and those collected from the experimental rig. Both model and rig simulate the type of sideband response depicted, which occasionally occurs in full-scale aero engine roughness testing. The results of the test indicate that in rotor systems having motion-dependent stiffness, discontinuities, aperiodic responses categorized by spectral sidebands may occur in certain speed ranges. These sidebands may give a divergent or fan-like structure of frequencies. Manipulation of the time history shows that the radial motion of the rotor may be periodic and that the spacing of the sidebands corresponds to the frequency of contacts between the rotor and the snubber stiffness. Furthermore, the spectral content of this type of response is derived primarily from cyclical changes in the phase between the force and the response, which occur because of the intermittent contact between the rotor and the snubber assembly. Acknowledgements. The authors wish to acknowledge the financial support given by the Ministry of Defense to facilitate this work and the support of the technical liaison given by the Bristol and Derby divisions of the Rolls-Royce Aero Engines Limited. References include Harwich, subharmonic vibration of rotors and bearing clearance. Harwich, stator whirl with rotors and bearing clearance. 1966-1967. Bentley D, subrotative speed of dynamic action of rotating machinery. 1974. Childs D, fractional frequency rotor motion due to non-symmetric clearance effects. Muzinska, partial lateral rotor to stator rubs. DW, nonlinear rotor dynamics analysis. Borthwick D, the numerical solution of transient structural dynamics problems with stiffness discontinuities. Borthwick, the numerical solution of discontinuous structural systems. Institute of Sound and Vibration Research. Nelson, dynamics of simple rotor systems having motion-dependent discontinuities. Once again, read about dynamics of rigid rotor mounted on discontinuously nonlinear elastic supports. Dynamics of a rigid rotor mounted on discontinuously nonlinear elastic supports.